Get ready for an awe-inspiring journey into the mysteries of the cosmos. From the birth of the universe to the cutting-edge discoveries of today, we'll explore the profound question that has captivated humanity throughout history. How did it all begin? Join us as we embark on an exploration of space, time, and the wonders that lie beyond. Are you ready to uncover the secrets of our existence? Let's dive in and discover the extraordinary origins of it all. Welcome to Revel Technology, where cutting edge meets limitless potential in the world of innovation. The question of where everything came from has long been a profound inquiry that has fascinated humanity. The idea that studying the universe itself could provide answers was once seen as exotic, but scientific advancements in the 20th century began to address the perplexities that had confounded philosophers, theologians, and intellectuals. Quantum physics, general relativity, and the Big Bang Theory emerged as significant developments, accompanied by remarkable observational and experimental achievements. These frameworks enable scientists to make theoretical predictions, but they also left unanswered questions, necessitating further investigation. In the quest to understand the origins of the cosmos, astronomers are currently utilizing the James Webb Space Telescope, or JWST, to delve into the early universe. Through this exploration, they have discovered a sense of emptiness in the extremely early stages. A pivotal moment in our understanding of the universe occurred in the 1920s when two sets of data coincided perfectly. Scientists, led by Vestos Leifer, had been measuring the emission and absorption properties of various stars and nebulas for several years. Since atoms are essentially the same everywhere in the universe, their electrons undergo the same transitions, resulting in identical absorption and emission spectra. However, certain nebulas, particularly spirals and ellipticals, exhibited significantly large redshifts, indicating rapid recession speeds faster than anything else in our galaxy. Edwin Hubble and Milton Thomson began measuring individual stars in these nebulas in 1923, establishing their distances from us. They discovered that these celestial objects were millions of light years beyond our own Milky Way. When the distance and redshift data were combined, it led to an unavoidable conclusion: the universe was expanding. This realization was also mathematically confirmed by Einstein's general theory of relativity. The greater the distance between us and the galaxy, the faster it appears to recede from us. This mind-boggling fact allows scientists to extrapolate the future of the universe as time marches forward. As the cosmos expands, galaxies move away from each other, with more distant objects receding faster. This expansion causes the wavelength of light to stretch towards the redder frequencies of the electromagnetic spectrum, resulting in what is known as redshift. Redshift is a crucial tool for astronomers as it provides insights into the physics of light and the composition of celestial objects. The farther away a galaxy, the further back in time we are observing it, with its previously visible light pushed into the near-infrared or even infrared range. This is why the JWST observes the cosmos at infrared and near-infrared wavelengths, as it is the best method for observing extremely early and distant galaxies. However, the same physical laws that tell us about the future of the universe can also reveal past events. If the universe is currently cooling, expanding, and becoming less dense, it implies that it was once smaller, hotter, and denser. Since its inception in July 2022, the James Webb Space Telescope has been providing spectacular images of the cosmos, including studies of the most distant and early galaxies ever seen. By observing the universe in infrared light, which is visible to the human eye, the JWST can detect faint light from old stars and galaxies, allowing it to literally look back in time up to around 13.5 billion years. Scientists are slowly gathering the pieces of this great cosmic mystery. However, how can they be confident that the galaxies they observe are truly so far away and from such a young epoch in cosmic history? Determining distances in space is challenging, and there is always the possibility that these galaxies could be closer and more recent. Astronomers employ various methods to validate their distance and time measurements, even for galaxies at the farthest limits of our cosmic horizon. The concept of the finite speed of light plays a crucial role in understanding this relationship between time and distance in space. Since light does not travel instantly, whatever we see, no matter how close, is actually seen at some point in the past. When looking out into the universe with powerful instruments like the Hubble Space Telescope, the Atacama Large Millimeter Array or ALMA and the JWST, the travel time of light becomes significant. Hubble allows us to see about 300 to 400 million years after the Big Bang, and as light traverses billions of years across the cosmos, various effects can impact it, which are critical in determining the age and distance of celestial objects. When ALMA examined the spectra of a distant galaxy, astronomers discovered a longer wavelength signal at 1,160 micrometers, indicating that it had been redshifted. This technique of determining distances in the cosmos is calibrated using spectroscopy, which provides information about the early galaxies. Spectroscopy leverages the fact that different chemical elements emit and absorb light at distant wavelengths. This means that the light from faraway galaxies and stars carries the unique signatures of the elements they are composed of. Scientists can compare what they observe in the cosmos with the wavelengths of light emitted and absorbed by specific elements in laboratory settings on Earth. For example, oxygen generates a characteristic signal known as OIII at the wavelength of 88 micrometers. By analyzing these chemical fingerprints of distant galaxies, astronomers can validate the period during which the galaxies are observed. The JWST has also made significant discoveries, such as identifying the universe's first known black hole. Scientists believe that many earlier black holes may have populated the primordial cosmos. The supermassive black hole, with a mass 10 million times that of the Sun, was found at the heart of a young galaxy 570 million years after the universe began. The JWST's powerful cameras enable it to see back in time to the earliest phases of the cosmos. This cosmic monster could be one of the numerous black holes that grew to ever larger proportions during the cosmic dawn, which started around 100 million years after the Big Bang and lasted a billion years. The origins and rapid growth of these black holes in the early cosmos remain a mystery. While some theories propose the existence of much younger primordial black holes that formed shortly after or even before the Big Bang, they have yet to be found. The formation of black holes is typically associated with the collapse of massive stars and their subsequent consumption of matter, but the sudden appearance of black holes in the early cosmos still puzzles scientists. The early universe was primarily composed of hydrogen and helium, with only a sprinkling of heavier elements known as metals, such as oxygen and nitrogen. The early stars and galaxies were considered metal-poor since there were not many heavy atoms to incorporate. These early stars utilized nuclear fusion to convert hydrogen into helium, and when they exhausted their atomic fuel, they could no longer withstand the inward push of gravity. The collapse of these stars resulted in significant supernova explosions, dispersing the created heavy metals throughout their host galaxies. The remnants of these stars became the building blocks of subsequent generations of stars, which were richer in metals than their predecessors. This process continues to this day, producing more metal-rich stars and galaxies with each generation. By examining the spectra of light emitted by a galaxy, astronomers can determine its abundance of heavy elements and estimate the age of the cosmos during which it is observed. If a galaxy lacks metals, it is likely from the early cosmos. As the James Webb Space Telescope continues to peer deeper into space, we can expect to uncover more about the origins of our universe and ultimately ourselves. The ongoing exploration of distant galaxies, the analysis of redshifted light, and the study of chemical fingerprints provide invaluable insights into the evolution of the cosmos. Each discovery brings us closer to understanding the profound mysteries of our existence. After delving into the depths of the cosmos and witnessing the remarkable discoveries of the universe's origins, what are your thoughts on our place in this vast expanse? How has this exploration of the cosmos impacted your understanding of our existence and the wonders that surround us? Engage with us by leaving a comment, subscribing to our channel, and clicking the notification bell for regular updates. Keep watching, stay inspired, and get ready for more exciting discoveries. See you in our next episode.